Hi everyone. It's 5:30 and we only have 45 minutes, so I'm going to get started. Thank you all for coming. My name is Alex Buckley. I'm the spec lead for the Java language and VM at Oracle. JDK 9 is here, and there's a lot in it. Some of the features are performance improvements, such as compact strings. Some are tooling improvements, like the search box in Javadoc that Mark showed in the keynote, and the new JShell tool. Straw poll, has anyone downloaded JDK 9 yet? Right answer. Has anyone played with JShell? Also the right answer. Is it the coolest thing ever? Yes, good. Some, of course, on this vast list are updates to existing features, such as support for Unicode 8. But the main feature, and the one that's taken many years to come to fruition, is the module system. The module system is a big deal because it enables modular development all the way down. The Java language and the Java virtual machine understand modules very deeply, so that the applications you write and the libraries you consume, and even the JDK itself, can all be developed and tested and packaged and deployed as modules with clear APIs and well-protected internals. Making everyone play by the same modular rules has great benefits for reliability, maintainability, and security, as we'll see in the rest of this talk. So with the theme of modules all the way down in mind, we've got three parts. The first part explains how modules are a long overdue building block in the structure of application code. The second part is about how applications and the libraries they depend on can migrate to modules. That is, it's about how you can mix modular and non-modular code. And the third part is about the structure of the modular JDK, including some of the compatibility issues that arise from that. So, programming in the large. In object-oriented programming, the basic unit of reuse is traditionally the class. Java has wonderful mechanisms for promoting reuse of a class: inheritance for reusing behavior, interfaces for reusing abstractions, separate compilation, dynamic linking, and access control down to the level of individual fields and methods. And we've had nested classes since 1997. So it should be possible for a single top-level class to encapsulate a vast amount of functionality. With that in mind, it seems that an application could be a single package containing a few very rich classes, all sharing data and fields accessible within the package, and where a handful of public classes form the entry points or the API of the application. Right? Not really. How many people work on a code base that consists of one package? Literally no hands. 2 packages? Just your own code base, not the dependencies. 3 packages? How many people work on a code base that is on the order of 10 packages? Some hands. 20 packages? Wow, this is going higher than it did at the last time I gave this talk. 50 packages? And this is just your own code base. Probably 300 or 400 in the front. That's why you're in the front row taking notes, because it's, yeah. So this has made my point far better than I could have made myself. Programs do not consist of a handful of packages anymore. Even the smallest microservice wouldn't be expected to fit into a single package. Programs are packages, not classes in Java. Unfortunately, the Java language kind of gives up once your program is bigger than a single package. Just imagine how difficult it is to control reuse within a really large code base. It says here, like the 217 official packages in JDK 8, but what's 217 to your code base? The only way to share code between packages is with the public modifier, but then you're sharing it with everyone. It's not surprising that package friendship in one form or another has been requested many times over the years. A package is a great way to organize classes, but most people wish there was a way to organize packages too. Modules let you do that. A module is a set of packages designed for reuse. This is a long overdue building block in the Java language. In effect, modules record the structure of your program so that the packages you want to be reused can be reused, while the packages you don't want to be reused can't be reused. A program built of modules will be more reliable than a program built from a loose set of packages in jar files that can access each other freely and that expose too many APIs to the outside world. In other words, in JDK 9, programs are modules. Here's a module that everyone will soon be familiar with, Java Base. It's the foundation of every Java program, like JavaLang object is the root of every class. In blue are the packages of Java Base intended for use by code outside the module. These are its exported packages. In red are the packages internal to Java Base. They can be used by code inside the module, but not by code outside the module. These are its concealed packages. A module is declared in a new kind of file called modulinfo.java. It gives the name of the module and its exported packages. By exporting the JavaLang package, it means that the public classes of JavaLang are accessible from outside Java Base, and a package that is not explicitly exported, such as com/sun crypto provider, is concealed. Its public classes are not accessible outside Java Base. So this is the first feature of modules in JDK 9, strong encapsulation. A module isn't just a set of packages, it's a set of exported packages and concealed packages. The public classes of exported packages are accessible outside the module. The public classes of concealed packages are not accessible outside the module. This means that access control is more powerful in JDK 9 than in JDK 8. In JDK 9, you can arrange for public classes to be accessible to everyone, or accessible only to other classes in the same module, or sort of a halfway house where they're accessible to classes in the same module and a limited set of friend modules. So if you're looking at public on a class declaration, it no longer means that everyone can access the class. Access depends on whether the class's module exports the class's package. Since Java Base is a module, let's reuse it with a module of our own. Here's a class in the package ComExample hello, very simple class, and let's declare a module for it, hello world, at the bottom in modulinfo.java. For sake of argument, let's export the ComExample hello package with the exports directive. Now you're probably wondering how the hello world module knows that it has a package called ComExample hello. After all, nothing in the package seems to point to the hello world module. It's up to the tooling to decide during development which module each package belongs to. In practice, your IDE will take care of it. You'll create a modular Java application and be asked the name of the module. Then every package you create will be part of that module. If you run JavaC by hand, then JavaC figures out which module each package is in. That's why modulinfo.java is at the same level as the COM directory. In other words, if modulinfo.java is at the same level as the package hierarchy, then JavaC treats all those source files as one module. The benefit of relying on tooling to decide module membership is that it's really easy to place an existing package in a module and immediately give that package the benefit of strong encapsulation. We don't want each and every class, like say hello, to have to opt in by declaring the module it belongs to. That would invite errors, such as classes in the same package trying to join different modules, and that's a big no-no for reasons I'll mention later. One more thing. The sayHello class imports the JavaLang package. Where is that package imported from? Now you might say, the answer is obviously Java Base, because you told me a minute ago that Java Base exports the Java lang package, and you're right in general, but how does the compiler know that? Should it search the file system looking for modules which export the imported package? What if multiple modules export the imported package? If we intend to reuse the Java Base module, we should document that fact. Actually, since we're writing a module ourselves, we must document that fact. This is the second feature of modules in JDK 9, reliable dependencies. A module isn't just a set of packages, it's a set of packages that reuses the packages exported by other modules. So the Hello World module specifies that it reuses the Java Base module with a requires directive in its module info.java. This means that code in the Hello World module can import any of the packages exported by Java Base. What happens if code in the Hello World module tries to import any of the packages concealed by Java Base, such as Sun Security Provider in red? Here's a real example of some code that does that. Glassfish 4.1. It doesn't run on JDK 9 because the VM throws in a legal access error. The error message is class com sun enterprise security provider policy wrapper in module unnamed module, don't worry about that, cannot access class sun security provider policy file in module Java Base. Now, a glance at the OpenJDK repository shows us that the policy file class in Sun Security is declared public. But because that package is not exported by Java Base, policy file is only accessible from code in Java Base itself. To be clear, in JDK 9, the Glassfish code cannot access this public policy file class at compile time or runtime. It's exactly like trying to access a package private class. JavaC gives an error and the VM throws a legal access error. Sorry, Glassfish, you'll have to find a supported API, not one of these concealed sun.star APIs. I'd like to return to the module info.java file that declares the Hello World module. It's really important to understand that a module exports packages, but requires modules. The reason is due to an old software engineering principle. The unit of reuse is the unit of release. This principle is ultimately about separation of concerns. You reuse someone's code, not by copy-pasting it into your own source tree, but by depending in some way on the black box artifact released by someone else. Now, in the Java ecosystem, there's no question that the unit of release is the jar file. That doesn't change with modules. A jar file simply carries the module.info.class file produced from module.info.java alongside the ordinary class files. We call this a modular jar. So when someone releases a modular jar for the Hello World module, it's reused by someone else writing requires Hello World in their own module.info.java. The reuser benefits from an explicit coherent API consisting of precisely the green exported packages, and the releaser benefits from strong encapsulation of concealed packages inside the module which support the exported API. So even if there's high coupling inside a module, there's loose coupling between modules, another good software engineering principle. Okay, so you're requiring Java Base from your Hello World module, and you've built a modular jar for your module. Where do you put a modular jar? JDK 9 looks for modules in the system image and on the module path. The system image is in the JDK installation directory. That contains Java Base and a few dozen core modules. The module path is set on the command line like the class path, except that the module path points to directories containing modular jars rather than to the jars themselves. So Java -p mods specifies that modular jars are to be found in the mods directory, and -m hello world specifies the module to run. The key point then about modules requiring each other is that the module system can check the requirements and validate that a modular application is sound. Once the compiler or runtime has found the initial module, hello world, in the system image or on the module path, it performs a process called resolution. Resolution means inspecting its requires directives and finding those required modules in the system image or on the module path, then recursively resolving them. We're building a graph whose nodes are modules and whose edges are the requires relation. And to be clear, in JDK 9 we do this at compile time and runtime. If resolution succeeds, you get 3 guarantees. First, every module that is required is available. Okay, pretty obvious, but a big improvement over the class path where you don't discover these identityless missing jars until later. Second, modules don't depend on each other in a cycle. Cyclic dependencies lead to code that is hard to maintain, and we're taking the opportunity to prohibit them in modules from day 1 of JDK 9. Now, some of you are thinking, this is just dependency management. Doesn't Maven do this? Who is thinking that? Some hands, okay, that's fair. Now, bear in mind that Maven only works at compile time, and this resolution process works at runtime as well. But more importantly, let me come to resolution's third guarantee. If code in one module imports a package, then the package is exported from exactly one other module. Now, this guarantee relies on exports as well as requires, so you won't find it in Maven. It means there are no split packages, which is what happens when 2 jars on the class path contain the same package, and you load some classes from one jar and other classes in the same package from the other jar. Split packages are a huge failing of the class path mechanism because they lead to very difficult to debug scenarios. Thanks to resolution, they're completely impossible in a modular application, which is obviously good for long-term maintenance. And this is what we really mean by reliable dependencies. The dependencies in a graph are reliable when each module can access only one version of a package at a time. The guarantee of no split packages is a big deal for performance as well. Because we know precisely which module exports which package, there's no need to scan every module in the system image and on the module path when trying to load a class. Contrast that with how you load classes from the class path. Here's the class path for Hadoop. The compiler or runtime has to do a linear search through 110 jars whenever a new class is needed. Of course, the implementation can speed things up by caching the classes it found when it wasn't looking for them, but there's still this nasty half here, half there problem of packages being split across multiple jars. How would you even find out that that's going on? If you think about it, the class path is pretty crazy. With 110 jars, there are over 12,000 possible interactions between classes in different jars, each one starting a linear search. The class path is the ultimate in erasure. Whatever you know about the structure of your application, the class path throws it away and connects everything to everything else. With modules, you are telling resolution what you know about the structure of your application, those requires directives, and it uses that information to provide both safety and performance at compile time and runtime. The prohibition of split packages in modules has an impact on application design as well. One reason that a package might have been split across jars was to allow different parts of an application to share package private code while allowing the parts to evolve independently. Now, these jars can't be turned into modules because they would all be exporting the same package. However, the module system has a better way to structure the application than splitting a package. Let me set up this scenario in a bit more detail. Assume all of this takes place in a pre-JDK 9 world. So, on the left, the application has an API intended to be globally accessible. It's the public foo interface in package P. The application also has some helper code, which creates or assists implementations of the API, ideally without being accessible by users of the application. It's the p-helper package. And finally, on the right, the application has implementations of the API, again intended not to be user accessible. Those are classes X and Y, which live in different jar files and implement the p.foo API. In order for the helper code and the implementations to work together, they need to be in the same package. The implementations are you would definitely make them package private so that user code can't access them. Now, the helper class, foo helper, is then package private too. It could be public, but then it will be accessible to users, and we don't want that. There's a bunch of problems with this setup, which is really the only way you had to structure an application prior to 9. For one thing, you've got to make sure that the implementations in the p-helper package don't tread on each other's toes. There can't be any class name overlaps between the implementations, since they all contribute to the same package, p.helper, despite living in different jar files. A second problem is that you can't make effective use of sub-packages. As these implementations grow larger, it will be natural for them to introduce sub-packages. But sub-packages can't access the package private code in p.helper. So you really would need a public class in p.helper to act as a backdoor for sub-packages living in the implementations. But then, of course, anyone in the world can get to the backdoor as well. A third problem, of course, is that anyone can make a jar with classes in the p.helper package and start relying on the helper code in the API jar and the details of classes X and Y in the implementation jars. What's really going on here is that the package p.helper is being overloaded. It started life as a simple namespace for code that helps the API. But now it finds itself being the unnatural home for all kinds of vaguely related things. What was the developer meant to do? In JDK 8, the only structuring mechanisms were classes, interfaces, and packages. Splitting the package across jar files was seen as acceptable, but you can see that it has a host of downsides. In JDK 9, the structuring mechanisms are classes, interfaces, packages, and modules. Modules take the strain of encapsulation and concealment so that packages can focus solely on being namespaces that are meaningful to the developer. So here's the same application developed as modules. Let's turn api.jar into a modular jar by adding a module declaration. I'm going to show it here. The module called API exports the package P to everyone. That's the main API. And exports the helper package, p.helper, to its friend modules, impl1 and impl2. The second export directive of p.helper is called a qualified export. Any module in the world can require the API module and access the package P. But only the friend modules can access the package p.helper. Now, I'm not showing the module declarations for the friend modules, but they will obviously require the API module in order to access the p.foo interface that they implement. The friend modules won't export anything, and they can organize their concealed packages as they wish. Now the p.helper package isn't overloaded with implementation classes from multiple jars. The naming of packages is much clearer throughout all 3 jars, and more implementations can be added smoothly. In effect, modules make packages as cheap as classes, and then control the reuse of packages very precisely. So, a module is a set of packages designed for reuse. They offer strong encapsulation and reliable dependencies. And the tooling, the command line tooling, the IDEs, will be a big part of modular development. Part 2. We'll talk now about how to take an existing application and migrate it to modules. Since it's impossible to modularize the Java ecosystem all at once, we're going to be living with a combination of modular code, that's modular jars on the module path, and non-modular code, traditional jars on the class path, for a while. That's fine, and JDK 9 can ease that migration. That's what this section is about. We'll start with a simple application that we want to migrate from the class path. At heart, a typical Java application has 3 layers. At the top are your application jars. There might be one or more of these. At the bottom is the JDK. And in the middle, there's a bunch of library jars downloaded from the internet and thrown on the class path. Does this look familiar to anyone? Some nods, yes. Now, I've hinted that we've turned the JDK into modules, and so in this part, green boxes will represent modules. You've already seen the Java base module, and you won't be surprised to learn that there are modules for logging, database access, XML processing, etc. Here they are. But our application isn't modularized, and nor are any of the libraries. Should we modularize our application? Obviously, it's up to you. You could just run it on the class path like you did in JDK 8. But we modularized the JDK for a reason, to improve security through strong encapsulation and stability through reliable dependencies. Applications might want to benefit from that just like the JDK does. So let's look at how we might turn the application into modules. Let's imagine our application is 2 jars with main code in myapp.jar and helper code in mylib.jar. Let's also imagine that the soup of library jars is limited to Jackson, the JSON processing library. Jackson comes as 3 jars, core, data bind, and annotations. And we have the modular JDK at the bottom. This is how we'd run the application today. We've got to set up the lib directory to include our application jars and the library jars and point the class path at them. Maven does this for me. Well, yes, but it does this, and it's good to know what it's doing under the covers. Then we run the application with the Java launcher. One of the things we gain by modularizing is not having to list dependencies on the command line. So let's look at one scenario for migrating this application, the top-down scenario. Here we first modularize our application jars without touching the library jars. Now, in general, if you're depending on third-party libraries, you are depending on them to modularize. And we can make it easier for libraries to modularize, but we all have to wait for them to do it. No one can force them. So it may well be that some of the libraries you depend on are not modularized yet. That's okay. For your application jars, the obvious path is to turn them one-to-one into modular jars, where each jar file has a modulinfo.class file. This is not always possible, especially if the application jars have cyclic dependencies between their classes, but let's go with it for now. If we're going to turn each application jar into a modular jar, we'll need to write a module declaration in modulinfo.java. Recall that a module declaration gives a name, and a list of exported packages, and a list of required modules. The names are easy. We'll call them myapp and mylib. But we don't yet know what each module depends on. We could make a manual analysis of either the source files or the class files, but there's a better way, the JDEPS tool. JDEPS scans class files or jar files and tells you what code from other jars they depend on. JDEPS actually came in JDK 8, and there's an improved version in JDK 9. So whilst this analysis, it can't be a perfect solution, it's a pretty good start. So we'll run JDEPS on the application jars with the Jackson libraries on the class path. We see that myapp.jar depends on 2 of the Jackson jars, which remember are none of these are modules yet, and of course on mylib.jar. Plus, myapp.jar depends on the JDK modules, Java Base and Java SQL. JDEPS knows if you're using the JDBC API that it's coming from the Java SQL module. mylib.jar, it turns out, depends only on Java base, so that's nice and simple. Now we have what's needed to write the module declarations. We'll start with the easy one, mylib. We know it depends on Java base. We can write requires Java base, and I showed that earlier, though actually we don't have to. It's always put in for you by the compiler, because every Java program ultimately relies on Java lang object. You can't write a Java program that doesn't indirectly rely on Java lang object. So you don't actually have to write requires Java base. It will always be put in for you. Now, from the JDEPS run, we know that myapp.jar depends on mylib. And if we'd run JDEPS with more options, we'd have seen that myapp.jar needs a particular package in mylib. So we could write exports for that package in this declaration to allow anyone to access the package, but as we saw earlier with the qualified exports, if we're sure that no one except myapp needs to access this com.myapp.util package, we can use a qualified export to maximize the encapsulation. Let's turn to the module declaration for myapp. It requires mylib, which we just wrote, and some JDK modules, Java base and Java SQL. And we know it's going to use Jackson, but we're not sure how to write the requires directives yet for Jackson because Jackson isn't modules. Does that mean that we have to turn Jackson into modules before we can modularize our app? That would be very unfortunate since we don't, I mean you don't control the Jackson jar files. If only there was some way for the Jackson jar files to somehow become modules automatically. We don't know what their dependencies and exports would be, but we have a pretty good idea what their names would be. They'd be the same as the jars, jackson.core, jackson.databind, and jackson.annotations. It's obvious from the jars. If we could do that, we could finish writing the module declaration for myapp. We'd have a lovely module graph with myapp depending on mylib and Jackson core and Jackson databind and also on Java base and Java SQL. The good news is that we can do this with automatic modules. An automatic module is a module whose declaration is inferred by the module system from a jar on the module path. So if we have jars that are not modular jars, we can still put them on the module path and the module system will turn them into modules. In effect, automatic modules are a feature that mean yesterday's jars are already today's modules. Once automatic modules spring into existence for Jackson core, Jackson databind, and Jackson annotations, the module graph looks quite different. The automatic modules basically say requires for everything. That is, they require each other and all the modules in the JDK and all of your modules as well. And they export all of their packages. Now, whilst this may very well not be the set of requires and exports directives that the maintainers of Jackson would write by hand, it's actually a feature because it emulates the behavior of the class path. It provides the maximum possible compatibility surface for code in jar files. And actually, overall, this is better than when everything was a jar on the class path. For example, if you look carefully, there's no arrow from mylib to myapp. So there is no danger of code in mylib accidentally reaching into the app's internals. On the class path, code in mylib.jar could access code in myapp.jar quite easily without even knowing it. And that's what causes maintenance headaches down the road. So when thinking about migration, each application jar is usually a good candidate to be a module. Each library jar will modularize at its own pace, but automatic modules mean you are not waiting for the weakest link. Now I'd like to turn our attention in this final section to the Modular JDK. 20 years ago, the Java platform was small, just a few hundred classes. And the organization of the JDK was not a problem. But every year the platform grew bigger, and now it's tens of thousands of classes. The JDK is huge, and worse, it's monolithic. Now, in reality, the Java platform is not one thing. It's more like 25 separate frameworks, including the Swing UI framework, a crypto framework, a scripting framework, multiple XML processing frameworks, and so on. There's no reason these separate frameworks have to be tightly coupled in one download. In fact, it's an impediment in developing the JDK. The overly tight coupling, perhaps accidental, raises development and testing costs, which turns into slower platform evolution. Plus, the larger the surface of your platform, the harder it is to secure. And it's an impediment to a lot of users, both those who want to run their applications on smaller devices and those who want to run more instances of their application on large systems. Even if you only wanted a part of the JDK, you had to take all of it. That all changes in JDK 9. We've taken the monolithic JDK and broken it up into a few dozen modules. Some are part of the Java SE specification, some are just part of the JDK implementation. Here's a graph of the Java SE modules. At the bottom, there's Java Base, which everything depends on, and which depends on nothing itself. We've broken out the various frameworks into their own modules: instrumentation, logging, XML, scripting, desktop, which you can require or not require as your needs dictate. There's a Java SE module at the top which has no code in it. It just has dependencies. So you can say requires Java SE and be guaranteed to have all of these modules available. Now, it's worth mentioning that merely finding these module boundaries and relationships, which might be obvious in hindsight, was a tremendous engineering effort. You'll find in your own code that decoupling a monolith is much harder than building a loosely coupled system from the beginning. The good news going forward is that the discipline imposed by modules will prevent all of us from accidentally recreating a monolith, from backsliding into the big ball of mud. I'd like to quickly review the expectations of compatibility from JDK 9. First up, there are various technologies from Java EE that ship in the JDK as well as in app servers. The list of Java EE modules in JDK 9 includes Corba, JAX-B, JAX-WS, and common annotations. These modules, which were not on I didn't have them on the previous slide to keep it simpler, but they are in JDK 9, are deprecated in JDK 9 and will be removed in a future release. Because of that, they are disabled by default in JDK 9. If you're running code on the class path, you may need to use the add modules command line flag to enable these Java EE modules. Second, a lot of tools and libraries try to access parts of the JDK that are meant for internal use only. Unfortunately, it'll take a while for tool and library developers to move away from this practice, so JDK 9 temporarily allows access to JDK internals, but prints a warning when it happens. Now, there's a command line flag to avoid these warnings, so please check with tool and library developers about how to deploy on JDK 9. Or just search Stack Overflow, where people have been asking for a few weeks now, why isn't stuff running? What is this exception? What is this warning? What do I have to do? And the answer is temporarily add opens. There are also miscellaneous changes in JDK 9 that are unrelated to modules, but might affect code that ran on JDK 8, and I want to be upfront about them. Notably, code that assumes the Java version string begins with 1 dot, or assumes that the JDK lives in a file called rt.jar, will fail on JDK 9. Again, please check with tool and library developers about which versions are needed to run on JDK 9. You can't assume that older versions of tools and libraries will run on JDK 9. So, in the modular JDK, it's modules all the way down. JDK internals are accessible temporarily in JDK 9, and you may need to upgrade tools and libraries to their JDK 9 aware versions. In sum, a module is a set of packages designed for reuse. Automatic modules assist with migration to modules, and you may need to upgrade tools and libraries to their JDK 9 aware versions. There is a huge amount in the module system that I haven't had time to talk about. You can encapsulate resources in a module, not just classes. You can express optional dependencies by programming with services. You can build custom system images with the JLink tool, so you can physically drop Corba right now if you want to. And you can spin up multiple versions of a library with the module layer API. If you're interested in this kind of thing, I recommend 2 books. The first is Java 9 Modularity, out this week. It's a pragmatic walkthrough of the entire module system and the modular JDK. And the other is Java Application Architecture from 2012. It is a principled look at constructing modular applications. It's nothing to do with JDK 9 or Jigsaw. And it has fantastic advice that applies whether or not you use this module system. OSGI is in the title. It's general advice about structuring large Java programs. So JDK 9 is here. It's on jdk.java.net today. If you're a library maintainer, please run JDEPs to see what JDK internals you rely on. You can do this right now, even on your JDK 8 installs. Everything you ever wanted to know about the module system is discussed in JEP, which is JDK Enhancement Proposal 261. I cannot emphasize enough how much valuable information lives in JEP 261. There's also JEP 260, which identifies the JDK internal classes that are temporarily exposed in JDK 9. JEP 223, which defines the new version strings beginning with 9. And JEP 220, which discusses how rt.jar has gone away and the structure of the modular JDK. And finally, JEP 200 gives an overview of the Java SE and the JDK modules. But if you've read JEP 261, there won't be any surprises, because 261's already talked about the modules and the class loaders and how you compile against them and patch them, etc. And with that, thank you very much. We have 3 minutes for questions. There was a question here, to be fair, that Alan, Mike, right, good, thank you.
In the keynote, it said that we're going to be going to a 6-month cadence. Does that mean that our warnings will become errors in 6 months, or?
Like with incubation, so the question is, if the JDK is being released every 6 months and we're printing warnings about temporarily allowing access to something, does that mean the clock is counting on a 6-month deadline? Nothing is ever set hard and fast. We don't say it's exactly the next release that it'll be the encapsulation will be dialed up, but in a soon, the future will be here sooner than we think. Let me put it that way. This video is available. You actually don't want the slides because you need the notes as well, so the video is the best thing. Yeah.
Hi. Is there any way to depend on a package without specifying the module?
Is there any way to basically require a package and not a module? No, the granularity of dependencies is module to module.
So you can have 2 modules that provide alternative implementations of a package?
You can do that with services. I commend to you my talk on Wednesday about services.
Okay, thank you.
There's a question at the very back. Oh.
Hello. So do you know anything about the future of OSGI regarding the modularization of the JDK?
No. Next question.
What about war applications?
Ask the EE4J initiative.
Okay.
Mr. Robert Schulte has a question. What could it possibly be?
So can you spend some words about migrating libraries and about the automatic module name?
The question is, what about migrating libraries? Libraries are just Java classes at the end of the day. If they so happen to call set accessible. Okay, quick straw poll. Who has used core reflection in their recent lives? Okay, to be fair, some hands. Who, including set accessible? Ah, it's like a set accessible support group in here. Okay. So I sort of want to ask you, what are you calling set accessible on, but we're out of time. So for libraries, if libraries are trying to define classes into the application class loader, they should create their own class loader. That's a specific piece of advice. Just to say, Sun Safe is still accessible in JDK 9. If you are using it for off-heap memory access, you should be using var handles instead, and then you should be using multi-release jars to put the var handle code in a separate directory for 9 than what you were doing on 8. And there could be entire presentations about that. Is there a specific, because no one here is a library maintainer, right?
No.
One hand, two hands.
Okay. Well, it's all about keeping the Maven ecosystem clean. So if you are a library builder, and you want to refer to jars which are not yet modules, please only refer to them if they have a module name with the manifest file and not based on their jar file name.
That is an excellent point that you gave me every opportunity to make, and I failed to do so. The point is that library maintainers, even if they don't declare a module explicitly, should indeed put it in their POM, and specify the automatic module name manifest entry. That is a way to commit to a name for a modular jar without actually putting module info class in the modular jar. And committing to a stable name for a module is a huge deal. And we encourage library maintainers to do that, even if they haven't looked in any way at the encapsulation story or the or what they're going to export or what they're going to require. Maybe one very quick question. Was there one there? No? One very quick question from the back.
Hi, we use the Java cryptology extension for like Bounce a Castle, and we have to sign that with a digital certificate from Oracle to be able to deploy that. What changes will have to be made to do that, if any?
So this is really a question about signed modular jars.
Yeah.
Alan can best answer that on the microphone.
Your Bouncy Castle should work as before. The security configuration file is slightly changed now in that you actually give the security provider name rather than the class file, but there's a backward compatibility that just keeps existing providers actually working. I can't give you the full answer on the signed crypto provider that's packaged as a module, because there's a couple of issues there that is just way beyond the scope of modules. But there's a security BOF tomorrow night that actually Sean Mullen is leading that will be an excellent place to bring this up.
Great. Thank you again.